Hi, my name is Jean-Baptiste Poline. I'm going to give to you like an introduction to the reproducibility in the life science lecture. So the lecture is divided into three parts. First, some background information. Secondly, we are going to look at the causes of irreproducibility and then look at what can be done to curb that problem. So let's start with some background. I think the key first study that generated some buzz and questioning on the reproducible science was the one by Amgen. This little pharma looked at 53 papers in preclinical cancer research. And they looked at papers that were published in very high impact factor journal, also had very groundbreaking results. And they, after 2 years, they tried to replicate those 53 papers, the various results in those papers. And they, after 2 years, they concluded that could only replicate something like about 6, so 11% of the results. And a bit more, they partially replicated maybe something like 20% of the result. So that study was really a wake-up call for the life science and especially, of course, for the preclinical cancer research communities. But in general, I think it was not. It was just one among many that were going to show that there is a reproducibility crisis in life science in general. In the neuroimaging world, this more recent paper showed that if you look at brain activity in unipolar depression, if you look at individual studies, you do find some association with some regions of the brain being involved in the unipolar depression. However, if you look at the meta-analysis across all those neuroimaging studies, there is no significant results revealed with this meta-analysis, again showing that individual studies may vary quite a bit, but the reproducibility aspect of the results in those studies is poor. In the imaging genetic, like a genome-wide association study here, performed by Jason Stein et al. In 2012. They looked at the association of the various single nucleotide polymorphism and the hippocampal volume, and showed that there is indeed a gene involved, a SNP and a gene involved in the hippocampal volume. However, they looked also at whether the previous results in this area were replicated, and showed that very in general, there's little association with the meta-analysis that they did across two very, very large cohorts and the previous results. So again, casting some doubts in the previous literature. So I think it's clear that there is a credibility or reproducibility crisis, not everywhere, and not all results are irreproducible. There are many good and solid results in the life sciences, of course. I should make that clear. But there is also like a large amount of too many results that are not necessarily very well reproducible. So this attracted the attention of the funding agencies that didn't want to waste money on the research that couldn't be reproduced, and I think the key first action was the NIH plan to enhance reproducibility in 2012 and 2014 by Collins and Tabak, and this has been also taken up and being sort of mimicked by a number of funding agencies. I'm thinking in particular to the Wellcome Trust. The Wellcome Trust has done a lot to try to cover reproducible results. So the problem is fairly widespread. It's widespread in the general news agencies, and the general public awareness is growing on this problem, but obviously also in the scientific literature. I would like to point to at least a couple of things here. One is this: why most published research findings are false, by John Ioannidis in Stanford. And this is an old paper, I mean, 2005, which is not very old, but it's been like more than 15 years that this paper has been published. And still we are struggling to make research more reproducible. The Lancet, for instance, had a very nice, interesting editorial on reproducibility a couple of years ago. And Nature and others, of course. So we have established, I think, that there is, at least in part of the life sciences, some irreversibility crisis or reproducibility crisis. And now let's go into some definition and terminology. So I've used the term reproducibility as a general umbrella for a number of problems. And I will continue to use it as a general umbrella term for different things. But let's go into the details of those different things a bit more. In this matrix here, you see, we've divided into code, analysis, and data. It's a kind of a classical matrix here, like I think I've taken that from one of Joel Espino's talk. And if you're using the same data and the same pipeline and the same code and the same analysis, usually people would talk about reproducible. Your results are reproducible because you can reproduce those things yourself. Or others can reproduce those things with your code and your data, and I mean, the code and the data being used. If you're using a different data set, but the same methodology, the same pipelines, then often it will be the term used will be replicability. So replicable results will be the same sort of methodology, same sort of pipeline on the different data set. If you're using the same data, the same data set, but you're using different pipelines, then often people will talk about robustness. But the key word here, I think, is the word generalizability, because it's really how much your result is going to generalize across a number of dimensions. One dimension is the data. Is that result going to replicate across many data sets and therefore is generalizable across data sets? One dimension is the code and the analysis method. Is that result going to replicate being robust with different methods and different software? And that's robustness. But you can think of different other axes of reproducibility, and therefore, like the generalizability aspect across those different axes is what we should be thinking about. Again, in this lecture, I will use often the term reproducibility as an umbrella term for all those things, but I wanted to give you the definition and the way those terms are being used often in the literature. So what are the causes of irreproducible research in life sciences? So I've divided the causes into three dimensions, three axes, three parts. First, poor statistical procedures. Second, issues in data and software. And then the third, more broad and more and harder to tackle cultural issue in publication practices and research incentives. So let's go to the poor statistical procedure part first. The one thing that sticks out really is the small number, the small size sample size. So taking this example from Melanjic in 2012, looking at on the x-axis at the year of publication, on the y-axis at the effect size, here in this instance, the association between BDNF, the dynamic variant, and the hippocampal volume, and looking at the size of the cohort being used in the various studies being reported here. So each circle here is a study being reported, and it's the effect size in terms of Cohen's d effect size here, reported and with as a function of the year of publication. And you see that small cohorts, indicated here by small circles, will show effect sizes of various variable effect sizes, while bigger cohorts will, in this instance, for this association, will show less variable and smaller effect sizes. So here you see like a very high effect sizes, almost more than one QLSC with a small cohort. And those things tend to be published because they tend to be significant, but they also tend to be not reproducible. And the small number of participants or in the study is really the problem here. This is another landmark paper that I really would like you to know about, which is the Brian-Nosek reproducibility of psychological science published in 2015 in Science. And Brian-Nosek and others have designed a number of replication of different results in psychology. And you're looking here at all those results in green that have been replicated, with on the x-axis the original effect size, and on the y-axis the replication effect size. And those green studies here show like a significant result that were the same as the original study. But all those red studies here showed like a much smaller effect size. And the size of the cohorts were taken to have sufficient power for like a replication, but some of them didn't have enough power, but so we can't really say anything about those things. But in general, a number of studies could not be replicated and had a much smaller effect sizes than the original studies. About 40% of the effects were stated as replicated. In a more recent, I mean, not that much more recent, but like in the neuroimaging world, there's this Podrak paper in PNAS in 2016, showing again the number of subjects being used in neuroimaging studies. Here, look at the year of publication on the x-axis again, and here the mean sample size obtained from the publications. And you see that the mean sample size of groups involved in a neuroimaging study is growing with the years. But in 2016, it was about like 25 as was the median. And if you look at 25 subjects, and look at what is the effect size that I can detect with 25 subjects, you find that this is about an effect size with 80% power. We find an effect size of about 1 in the QLSC. However, if you look at the effect size that is actually found in neuroimaging data, here the HCP data in the different activation studies, you look at even for strong cortices, strong activations, like for instance, motor cortex or SMA cortices, you find like an effect size of about 0.6, 0.7, which is a very strong effect size of very robust activities. And therefore, in other activation studies, you may have like a smaller effect size that will lead to. So those effect sizes are hard to detect, and when detected, they may not be always replicable because of the we don't have the power for detecting those things according to the study. So power issues are really critical. So power again is the capacity of a statistical test to detect the probability of the test to be significant when the alternative hypothesis is true. And this and having a small power and not being able to actually have that high probability of that detection when there is an effect of there is an actual effect in the study is really what is driving some of the reproducibility aspects in life sciences. And those again by showing some very high effect sizes sometimes that are purely due to randomness of the sampling. In this Botvinik-Nezer paper, they describe that the average or the median power of studies in neuroscience is something like around like 40% of power, which is very low probability of detection, and therefore the probability of refinding a significant test later on, what's the probability of that hypothesis? Basically, the probability of the hypothesis to be the alternative hypothesis to be true, given that the test is significant, can be quite low with low power. So this, for instance, with 10% power, even if you find a significant test, there's a very low probability that your alternative hypothesis is true. The bias as well, the amount of the effect size that you find can be very high if you have low power as well. So that's what this Botvinik-Nezer importance in Nature Neuroscience is showing. And one of the key really paper in this framework is the Untitled paper, why most published research findings are false. And Untitled was looking at what I described before, the positive predictive value, the probability that the alternative hypothesis is true, knowing that the test is significant. So if you look at that probability with low effect power, with low power studies, you do find a low PPV, a low positive predicting value. If you think that this is a problem just for the framework of null hypothesis testing, which I'm using here, this is not true. I like this very interesting study by Gail-Varrocco et al. In 2017, show that for machine learning, the sample size is also a problem. For instance, looking here at studies that will show the accuracy of prediction for a specific diagnosis in the psychiatric or neurological disorders. You see that the so the size of the cohorts is in the x-axis here, and the accuracy is in the y-axis. Show that accuracy is the y-axis. You should like the accuracy even with cross-validation framework. Accuracy can be very strong with low sample size and then go down with like a higher sample size. So this loss of accuracy in a number of studies with the increased sample size is something that really mimics what has been shown in the null hypothesis framework as well. So high effect sizes, if you want, with a small sample size, and large and smaller effect sizes with larger sample size. So the Untitled paper is really showing that if you are looking at the probability of your alternative hypothesis to be true, so is that there is indeed a result, that there is some effect, that probability can be low with low power, as stated previously, and this is a graph showing how power is influencing that positive predictive value that I'm defining here, the probability of H alternative being true, knowing that the test is significant. I'll go over those things in the module of statistics. So if you're interested in going a bit more in the details of those things, please follow the statistic module. If you are, this is under this left panel here is under the hypothesis that we have a type 1 error of 5%. If your type 1 error, the risk of error of type 1 error is actually greater than 5%, let's say 20%, the PPV, that probability is even lower, and you get maybe something like a 30% probability of having H alternative being true if your test is significant. The classical inference statistical framework is also was also a bit under the problem of what is called the p-hacking. So what is p-hacking? P-hacking is really trying to alter your procedure such that the p-value that is produced by a statistical test, a null hypothesis statistical test, is below 5%. So this really key paper by Simmons and Nelson and Simonson show that if you're using just what seems to be legitimate variation of analysis of your data, you may increase the risk of type 1 error by a lot, and therefore the 5% threshold that is being used for as a safeguard is not actually is not correct. It's you have a type 1 error, or much bigger type 1 error. If you have a variability, if you're trying several different analyses and then pick the 5%, the p-value that is the smallest. P-hacking, and I'll describe what is harking as well, is usually being done in good faith. This is not people or researchers trying to do some fraud. It's really researchers that think, okay, I've analyzed my data, they don't show significant results, but maybe I've forgotten a covariable, maybe I should have excluded more outliers. Maybe there's an interaction that I haven't modeled in my analysis, and so on and so on. So the various different aspects of the analysis that you're doing when you're analyzing data, if you're trying those things and then pick up the smallest p-value because you believe that's the actual correct analysis, that is what is p-hacking in good faith. And is definitely a problem across the board, because journals require that, or often require that, to have like a significant result to be published. There's a cost to seeing data, which I would like to alert you to. As soon as you start to look at your data and see, and if you haven't like a pre-registered hypothesis, and I'll go for that, it's dangerous to look at to start to explore the data before you're doing hypothesis testing, because then you have like a biased hypothesis if you want. Harking is hypothesizing after seeing the results, and it's basically the situation where there's some little bit unexpected results found in the analysis. And then you look at the literature and find some, and because the literature is very vast, you are likely to find some papers that might be related to those a little bit of unexpected results, and therefore you reformulate your hypothesis in terms of those results. So that's hypothesizing after seeing the results, or harking, which is also probably done quite often in good faith. I'm thinking, okay, I should have done this hypothesis, but you can't anymore when you've seen the results. So this concludes my little section on the statistical issues, and again, different things that are often done in good faith that we should be aware of. The second part in the causes for reproducibility is really the issue in data and software. So I'll go over a couple of things here. First, as an introduction and as a motivation aspect, I would like to describe the story of this researcher, a good researcher, who used a software that was inherited by another lab, a good lab that were publishing good papers, and this researcher working in crystallography was using this software and realized after a few years and publishing very high-profile articles in PNA, Science, and so on, that the software that he was using was actually flipping the protein structure and mirroring the protein structure, and therefore all those papers had to be retracted. So that software was inherited from someone else and also was passed on other laboratories and distributed. So I think it's a cautionary tale that like checking the software that you're using is one thing that should be done regularly, but unfortunately those software are trusted because they have been used before, and we kind of like assume that those have been tested often. There's a very interesting and prominent story about the Potier et al. And Duke scandal that is a complex story. So I'm not going to describe it in full at all in this lecture. I just want to point to one aspect of it. So this study was Bagley and Coombs were our biostatisticians that were asked by their biological colleagues or life science colleagues to help them implement results or methods used in Potier et al. That were publishing in very high-profile journals. An interesting method, and when they tried to replicate and they tried to investigate what the method was and so on, they realized that the results were published were wrong. And the reason why those results were wrong seems to be that a software was used to associate two CSV or two Excel spreadsheets, if you want, and those Excel spreadsheets, one of them needed to have the header lines, like and one of them needed not to have the header lines, and therefore there was a mistake, of course, done by the researchers, and therefore all the lines were shifted by one in those CSV files, and therefore all the association in this instance between the genes and the patients and were wrong, and this is interesting because they could find the mistake because the data were available, but they had a forensic analysis of it, and I think it's really interesting to look at that paper. They really had to kind of dive into and try to reconstruct how was those results produced, and so it's a very interesting story in that respect. I really recommend that you learn about it a bit more. I think honestly, I think that first mistake was probably just an honest mistake, and then there was some fraudulent aspect. But I don't really want to focus on that fraud aspect in this lecture. I don't think that's the most common at all problem in the irreproducibility aspect of life sciences. So Bagley and Coombe, conclude that most common errors are simple and most simple errors are common, which is a very insightful conclusion to their paper. Across OS, and so this was a motivation for a software aspect. I'd like to go a bit of across OS and across operating system and across implementation. Showing you some results from Tristan Glattard published in 2015 Neuroinformatics here, and here the difference of two different the difference between classification of the brain matter in either like the gray or white matter, and so the exact same pipeline, the exact same software being used on two different operating system versions was showing that difference in the segmentation, in the classification of the tissue, which is a little bit puzzling. And Tristan and others managed to find out that this was due to some numerical errors in the C libraries that were not the same on those two operating system versions. In a completely different setting, this is an example in machine learning taken from Joel Pino. Here, like showing that different algorithms implemented by different laboratories give a very different results across across implementation. So our first example was exactly the same software being run on two different operating systems, two versions of the same operating system. Here it's really two different implementations of the same algorithm that show very different return of average return in this instance in a machine learning area. Across parameterization of software and across software, I think I want to take the example of the cluster failure paper that was published in PubMed in 2016. We're showing that if you actually use some methodology, like a theory that's called random field theory, if you use it to detect activity in the brain using a cluster threshold technique, if that cluster is defined with like a low threshold, you end up like having a lot of false positive in a null dataset where there's no activity at all to be detected, and that's so that's really like the use of that theory of those software. Depending on how you define those clusters, is going to be more or less correct or very biased and give a number of type 1 error, which really points to the teaching of the limitation of a specific algorithm or specific framework, theoretical framework. Here, it's the difference found in the size of the left caudal intercingulate, a specific structure in the brain, across different software, work by Erin Dickey and others, showing that if you use the software ends to define that size of the intercingulate, or if you use the free surface software, you find a very small correlation between the values of those region of the volume of those regions across different across participants, which is worrying. You get a much better correlation, of course, if there's the same software with different versions of the same software. And the same sort of results, to some extent, have been found not only in the segmentation and volumetric measurement of brain regions, but also in activity of the brain using BOLD, using fMRI. And here you look at the average of the t-statistic across 3 different software, so AFNI, FSN, and SPM. And you look at on the x-axis is the difference of those of the t-statistic found by those software, and of course there's a lot of high and t values being found here, and on the y-axis is the sorry, on the x-axis is the average of the t-statistics, and on the y-axis is the difference of those t-statistics, and you see a very large difference of the t-statistics across the different averages. And those kind of difference in results in packages end up being showing different results in terms of in natural studies. So, for instance, here the study by Kadewal et al. Showing that across between ASD patients, autistic syndrome patients, and control, the variation, the difference of the size of the brain is shown to be significant. Or here the total intracranial volume of the gray matter, the white matter, the CSF, those sizes, those volumes are different, and some of them show some actual significant difference in some software, and then don't show with other software. So those variation in software results actually do have an impact on the results of studies. And the last aspect I want to talk about in terms of software, the vast variability of the pipeline, the flexibility of pipeline. And this is a key study by Joshua Karp, showing that if you look at the way you analyze fMRI data in the literature, and if you replicate all those possible ways for one study, you will find that all those possible ways are going to show activity, the maximum activity found in the brain to be at very different places. So although this is exactly the same data, just the variation of the analysis that have been found in the literature is likely to produce fairly different, sometimes very different results, and sometimes very close results, of course. This is a much more recent study by Botvinik-Nezer and many others, showing the result. If you take one data set, you send that data set here, like an FMRI data set, a bold data set, you send that data set to 70 independent laboratories, and you look at and you ask them, okay, give me the results on this hypothesis 1, 2, 3, 4, 5. Like what's these are my questions. What are your answers for those questions? And I will leave you entirely free of how you analyze the data. So no team had actually the same pipeline, but you see like there's those teams here like are represented in this box, and the cluster here show how close the results were across teams. So you see there's 3 different cluster, kind of one large one and 2 smaller one here, showing different that some teams find like a fairly visibly close result, and some teams find very different results. But even within a cluster that seem to be showing the same sort of results, you actually within cluster, the some of the hypotheses, the probability of the hypothesis to be said to be true, to be inferred to be true, is very low in that specific for that specific question here. So the probability of that hypothesis to be said to be true is only like 40%, almost 40%. And you see the difference of the map of the neuroimaging maps that have been that are shown using this in the 3 clusters, and they are very different indeed. The same sort of analytic variations in anatomical data is also showing very different results. Is also showing that the variability in the process of how you analyze the data, the analytical data, is showing very different results. I point to you to the analytical flexibility by Nikhil Bhagwat and in 2020 in my lab, and showing how different the software give results that are fairly far apart in this instance for like the correlation between brain regions in terms of their volume. We've talked about BOLD quite a bit, so fMRI. We've talked about T1 images and anatomical information. There's also the anatomical information of the diffusion data. And this recent paper shows that if you give, again, the same data set to different groups, so here instead like 42 groups, and you ask them to give you back some of the white matter bundles and the tracks between brain regions across the brain, you see very different result as well in the diffusion aspect for many different tracks. So the same sort of questioning of anatomical methodological variability is happening in the diffusion analysis as well. And last, to conclude that section, I would like to point to some of data issues. Just to remind you that issues in the data themselves, and not only of how we use and what kind of software and the flexibility of analysis of software and methodological flexibility that's not only the only problem. The data themselves may not be entirely adequate, of course. So one of the usual things is, I mean, can we reuse those data, which is starting with is there a license, that is there like a data usage agreement that I can look at? But often the data themselves don't have exactly what they claim to contain. So the database is not you know, up to date, or is not, documentation is not up to date, or the QC, the quality check, is wrong or is unreliable. Sometimes the header files are not correct, and there's a classical a huge problem that we had in the neuroimaging world when it was unclear how we knew what was the left side or the right side of the brain. The provenance of where those data are coming from is lost, so you don't actually know exactly where the data are. And there's a very nice video on YouTube that I really recommend that you take 3-5 minutes to watch, which is the on the provenance and labelization of what are the data, and how can you reuse those data if they are not clearly labeled. This is one HTTP at some stage released some of the free software 7.x data, and it seems that there were issues in those data. So the free HTTP people were saying, I would recommend to stick to the free software 6.0, and so those things happen. And so if you look at data sets or on the web, you really have to be careful of the provenance of the data set. The last section of this, what are the causes of reproducibility, is about the cultural issue and about the publication practices and research incentives. And I think the key aspect in that section is really that publication has been a very a bit too strong currency in research and evaluation of researchers and universities. So the high competition inside researchers to possibly keep the data and the codes as assets so that they can compete better with their colleague, and to publish a lot and get many authorship because that's how they are evaluated by their universities or the grant agencies. So the current incentive somehow kind of promotes not too reproducible research and more exciting research, but not as reproducible as we wished it to be. So there's a lot of push by many instances, many organizations to try to curb that issue, but still like pervasive. I mean, like I'm pointing to that specific paper showing that if clinicians are asking for advice from biostatisticians, there's often those biostatisticians are asked to do some violation of violation of the statistical principles, if you want. So and that happens frequently as well. So there's like a strong push to not follow the good practices in statistics to make sure and make sure that there are some results that are publishable. In this slide, I'm showing like what Dorothy Bishop would call the vicious circle of science, where there's some published or data that generates some hypotheses, and then there's a number of possible problems. One of them that described in depth, which is the low statistical power, so small sample size. And then when you collect data, you may be applying some of the p-hacking issue practices, and then again, and when you are interpreting data, you may be interpreting through a Harking aspect, and then you just generate a new experiment using those biased or poorly controlled results. So what can we do? I've described too many problems. What are the possible solutions? Where can we start to curb the reproducibility aspects of research in life sciences? So I've divided into 3 different axes again for this section. First, improve the training, and I should say improve training and awareness. I think and part of my talk is really of this lecture is really to raise the awareness of the problem. Also, develop better tools, better standards, and if we can, change a bit the culture and the environment for the incentive of research. So p-hacking solutions, for instance, specifically, well, you can pre-register your study, basically saying, hey, if I know what is my hypothesis, I'm going to tell you exactly how I'm going to analyze the data, and then I'm going to publish those plans and send those plans to a journal. I will say, all right, okay, that's a good and interesting hypothesis. The methods that you want to use is appropriate. We're going to let you do the study, and whatever the results are, we're going to publish those results, even if they're not significant, and which is the key aspect. There has been other solution being proposed by the community. There's even a journal that tried to ban p-values, so you can't p-hack them. They're not allowed anymore. I think that's extreme. There's the change of type 1 error, the alpha threshold of the type 1 error. So instead of like having a 5%, this, for instance, Johnson et al. Paper was saying, hey, you should really use a 5 to 1,000 rather than 5% threshold, and so on. So there's a number of the key, I think, aspect is really to complement the p-values with other statistics. Again, I'll go over some of those things more in details in the statistical lecture. Pre-registration is really promoted by many now. It's simple. It really does not preclude exploratory analysis. You can also do some exploratory analysis, but what you can't do is to generate other hypotheses after having seen the data. You can do it yourself, and really there's almost no reason not to do it if you are in that sort of framework for your study. And you can do it through OSF. OSF has the Open Science Framework has a good system for doing this. The other thing is that in terms of open science, reusing software that have been tested and collaboratively developed and have a good test suite is one of the things that you could do to try to make sure that you're not using a software that is not being tested. The aspect of standardization is also important. So there's a real rise of what we call fair containers, so containers that contain software that is well tested and can be applied a little bit with confidence. But of course, you should check by yourself. And that's also been like in the brain imaging world has been given the rise to the bit standards with the where you know exactly how the data are organized, so you have less interpretational problem less problem of interpreting what are the data, and you know that those containers, those software will run exactly as they should be on the data that have been normalized in the bits way. There's less action but there's still some action, and more people will try to also describe the provenance of how those data have been analyzed in a standard way using, for instance, W3C standards. The aspect that really I think we should all concentrate on is making sure that the study, the training is well done in terms of reproducible research. So increasing the awareness, but also increasing the tools and the training on those things. Those include three sort of areas: the computer science aspect, being very literate in that aspect, the math and statistical aspects, machine learning, but there's also the subject matter, knowing exactly what data you have, and having other ways of checking things, different ways of checking things. And if you want to publish, then you also have to know a bit on what is a fair way of, by fair, like a findable, accessible, interpretable, reusable way of publishing research objects. The Reproducibility Center, for instance, is trying to develop some of those educational modules to do some reproducible neuroimaging computation, which I'm showing you here. And those modules are very much in have the feeling of the data carpentry or software carpentry training modules, also the Neuro Academy Week training modules. So I recommend that you have a look at those things if you are interested. And then the last thing is really, can we change the incentives, not only do better training, but also on visible research, but also change the incentive such that we are going to do more reproducible research because the culture is actually targeting that goal, and publishing things that are not only exciting results that have a p-value of less than 1.05, but also the actual full research objects. So in this instance, for instance, publishing a data set that you spend a lot of time acquiring and organizing and putting a lot of documentation and so on is one of the way of we can incentivize a better, more replicable and reproducible research using those published research objects. For instance, here in scientific data, publishing a data set is a possibility. So in general, when you see a paper that have like some conclusion on the what really you want to dissect and see is how can I go back to those conclusions using the research objects that have been published with that paper. So for instance, here, what is exactly this increase in resting state connectivity? How is that? What is the anatomical framework? What data have been used? Can I reuse the data? What pipeline has been used? Can I reuse the pipeline? Can I reproduce those things on another data set and replicate, and so on and so on? So publishing the full research is what is necessary. So and publishing things that are not too general. So if your paper was talking about functional connectivity in autistic children, then it's really the exact data set and the exact methodology that is giving you a specific result. And that's for others to replicate or make sure that that result is robust with respect to the methodology. So we need to publish more than just the PDFs, really. And we need to incentivize researchers to publish more than just the PDF, but publish the data set, the pipelines, all those things. So that publication process can be done, and we are working with the OHBM, for instance. We're working on the Aperture publishing platform, which is targeting to a publication of different research objects, not only the PDF, but also the code, the data, and so on. With this, I would like to thank you for your attention, and hope that lecture on the introduction to reproducibility in the life sciences has been interesting, and please don't hesitate to send me any questions you have. Thank you very much, and this is thank you for many of my colleagues.